Let's begin the tutorial by introducing acceleration as a scalar and as a vector. Unlike speed and velocity and displacement and distance, we use the same name for the acceleration as a scalar and for a vector. So we shall say that A is the acceleration, and then we'll denote scalar. But then we shall also write the acceleration vector, which will be equal to an acceleration in the x direction plus an acceleration in the y direction plus an acceleration in the z direction. In this tutorial, or in this part of the tutorial, we are only going to look at the 1D scenario. So we will simplify our acceleration vector to be a subscript x hat in the x direction. These vectors were outlined in the previous video, so check that out if you are unsure. And we shall denote acceleration and this time as a vector. Let's move on to an example. Firstly, we're going to draw an acceleration time graph using the acceleration scalar. And so we draw our y-axis to be a for acceleration with the units meter per second squared. Then we draw our x-axis to be time with the unit seconds, and we draw our origin. From our example, you can see that the important times go up in multiples of 5 seconds up until 30. So we should draw on our times here. Firstly, we can see that our car accelerates from t equals 0 seconds to t equals 5 seconds, which means we have a positive acceleration going from these two times. Let's mark on our 5-second mark first. Then we can draw a straight line for our constant acceleration. After this, the car stays at constant speed until 10 seconds. 10 seconds is this point here. When our car stays at constant speed, it means the speed is staying the same, which means there is no acceleration, which means the acceleration on this graph will be 0. So therefore, we would simply draw a line along the axes. However, of course, you can barely see us, so we can just leave it blank. In fact, I'm going to draw a dotted line so you can tell where the acceleration goes to. It's okay to have these sudden drops in an acceleration time diagram. From 10 seconds to 15 seconds, the car decelerates. Once again, as this is only the scalar acceleration, it means an acceleration in any direction will always have a positive value. Therefore, if we are decelerating, we can just draw another straight line. And then I will join it up with a dotted line to the bottom of the graph. And we shall mark 15 seconds on here. The car then decelerates and stops until 20 seconds. If the car has stopped, then obviously there is no acceleration. After this, the car reverses, which means that it accelerates backwards until t equals 25 seconds. But obviously, this means that there is a magnitude of acceleration, meaning we can just draw another straight line. As we haven't denoted how strong the acceleration is, I can just draw these lines in any position. However, in an actual example, you may be told the actual value of the acceleration, which means you need to be more careful. This shows our acceleration going backwards from 20 to 25 seconds. Lastly, the car is going to immediately brake and come to a halt at 30 seconds, which means it's going to have to decelerate by the same amount it accelerated in order to come to a complete stop. Once again, no matter what the direction, the acceleration only has a positive value for the magnitude, meaning that our line actually continues. And then our acceleration will stop as it comes to a halt by 30 seconds. So we can draw a dotted line down here. This may look confusing, but this is because we've lost a lot of information when drawing an acceleration scalar graph rather than an acceleration vector graph. Let's move on to the acceleration vector graph. We're going to draw AX with the units meters per second squared. Then we're going to draw T with our unit seconds, and then mark on our times of 5, 10, and multiples of 5 all the way up to 30 seconds. The beginning is going to look very much the same, as we have an acceleration from t equals 0 to t equals 5 seconds. This will be denoted by a line, as our acceleration is positive going in the forward direction. The car then stays at constant speed until at 15 seconds it begins to decelerate, stopping at 20 seconds. This is where the difference between the two graphs comes in. If we're decelerating, then now we're working with vectors, we can draw the acceleration going in the opposite direction, meaning that now our acceleration could be down here. And then we'll draw a dotted line to join it up to the rest of the graph. This shows the obvious difference between accelerating and decelerating, which isn't shown in a normal acceleration time graph. There is then no acceleration between 15 and 20 seconds, as in the other example. Next, the car reverses, accelerating until 25 seconds from 20 seconds. Now once again, the car is now reversing, meaning the acceleration is in fact backwards, which means once again, we go to the negative part of the graph. We can then draw our line to 25 seconds before joining it up. After this, the car then brakes, decelerating to a halt at 30 seconds. Because our car was reversing initially, in order to brake, the acceleration must be in the forward direction, meaning now we draw our acceleration up here, because braking will have to occur by trying to make the car go forward. This is where the difference between the two graphs comes in at its best. Now, in order to brake, we need to oppose the acceleration that caused it to start moving, which is this acceleration down here. Therefore, our braking acceleration will be in the positive part, as it's stopping the car from going backwards, meaning we draw a line here, before joining it up again, before finishing at 30 seconds. You can very clearly see the difference between the acceleration vector graph and the acceleration scalar graph, and you can see that there is information lost in the acceleration scalar graph over the vector graph. Welcome to the simulator part of the tutorial. Here we have a wheel that's about to roll down a hill. This hill is on the exoplanet TRAPPIST-1d. The wheel will roll down the hill according to the gravity of the planet, and then we're going to draw the x acceleration time graph and then analyze it. So initially what you might see, which wasn't in the distance and speed videos, is that we actually have a very complicated graph here. And then over the top, I've drawn a rough interpretation in blue, which shows the general trend. Let's start off with the elephant in the room, which is all these immediate spikes. This is actually because the acceleration is directly proportional to the force. This is not something you need to know for this tutorial, but will be covered later on in another tutorial. The important thing here is seeing the general trend of the acceleration. However, the questions that we do will be much simpler. As you can see, in the first 4 seconds of the animation, the acceleration in the x direction, which is pointing down the hill, as seen on the video, is always positive and barely ever negative. This makes sense, because the wheel is rolling down the hill, which means it's going forward in the x direction, which means it must experience an acceleration. Once we get to 4 seconds, onwards until about 6 or 7 seconds, we get a negative acceleration trend in the x direction, or a deceleration in the x direction. This is when the wheel has reached the bottom of the hill and then starts heading up the hill, meaning that gravity is working against it. This means that in fact the x velocity will slow down. Once we reach 7 seconds and further on, we once again see a slight acceleration, but to be honest, it mostly just begins to flatline when the wheel stops. This great increase in acceleration is most likely when the wheel tips on its side. Above, we have an x acceleration versus time graph. Firstly, we need to read off the values of the acceleration at certain points in time. This is very simple. Let's find the acceleration at 1 second. We go to 1 second on our graph, and we see it corresponds to this point here, which corresponds to an x acceleration ax, which corresponds to 4 meters per second squared. Part 2, we need to do the same for 3 seconds, which is this point here, which corresponds to minus 2 meters per second squared. And then finally, part 3, we need to find the acceleration at 5 seconds, which corresponds to this point here, which has an acceleration of minus 1 meters per second squared. Very simple to begin with. Next, we need to find the velocity at 6 seconds. We shall write this down to show the change in answer. We need to find the change in velocity, or find the velocity at 6 seconds. You may remember from early on in the video that the velocity is equal to the acceleration times the change in time, which is also equal to the area. Therefore, we can say down here that the z velocity is equal to the area of the graph, A. Now, one important thing to remember is that the area will have a certain sign depending on its relation to the 0 point on the graph, meaning anything above the 0 acceleration mark will be a positive area, and anything below will be a negative area. So therefore, I'm just going to draw lines down here, and then we can begin to highlight out the areas we need to consider as such. We're going to call them A1, A2, and A3 respectively, where A1 goes between 0 and 2 seconds, A2 goes between 2 and 4 seconds, and A3 between 4 and 6 seconds. Now these are just squares, which makes it very easy to calculate the area. Area 1, we do the base times the height. The base is 2 seconds, and the height is 4 meters per second squared. 2 times 4, very easy. Next, we add area 2, which once again has a base of 2 seconds. You see between 2 and 4 seconds as such. And then we're going to say it has a negative height as it's below the 0 acceleration mark. And so a height of -2 essentially. You could also see that it goes between 0 and -2 and explain the -2 that way. And then finally area 3, we also have a 2 second base, that's normal, and now a -1 on the acceleration. This is going to give 8 minus 4 minus 2, which gives a final z velocity of 2 meters per second, which means that after all of this acceleration or deceleration, i.e. an acceleration for 2 seconds and then some deceleration for 4 seconds after at various magnitudes, we end up with a velocity of 2 meters per second. This could be seen as somebody accelerating and then holding down the brakes for 4 seconds, but eventually, after all that time, the car would still have 2 meters per second in this example. Thank you for watching this video tutorial. Visit my website coherentphysics.com for many examples with fully worked solutions.